Okay, AP Physics. This is going to be Unit 4, Work and Energy, the student workbook 4.I, Gravitational Potential Energy. Scenario goes as follows. An astronaut is lost in space near an alien planet and its orbiting moon, shown at the right, not to scale. At a particular instant, the moon is directly opposite the astronaut on the far side of the planet, in line with the center of the planet and at a distance r from the astronaut. So if you look at the picture, they've got the astronaut on the left side, the planet is smack dab in the middle, and then on the right side is the moon. Let's see here. For part A, it says mark an X on the diagram shown to indicate the location where the astronaut could move so that she would feel no net gravitational force. All right, so anywhere to the left is not really going to work because if they stay at the position that they're at now, there would be two pulls, one from the planet, from a Newton's third law pair, and the other one from a moon that's a Newton's third law pair. So anywhere to the left of that planet is a really bad idea. We don't want to go towards the larger massive object, so if we picked right here, this wouldn't work because according to Newton's universal law of gravitation, F equals big G little m big M over the distance squared. We have the large mass. If you're closer to the large mass, it's going to leave a lot larger pull since you're closer to a distance from that center of mass. So if you have a larger mass going on that shorter distance side, then that's not a good place to have it either. You know, even if you put it right here in the middle between the moon and the planet, the larger mass is still going to pull more towards it. So we need to set up our location to be somewhere that is closer to the moon and further away from the planet itself. So if you were to pick any distance between that halfway point closer towards the moon, that would be an ideal place where the gravitational pulls would cancel each other out and you would have no net force between the two. So that would be the location that we're looking for there. Let's see, if the planet was not between the astronaut and the moon, but the distance r was the same, would the gravitational force on the astronaut by the moon increase, decrease, or stay the same? Okay, so we have to be careful here with what it's asking us because it says if the planet was not in between the astronaut and the moon and the distance r was the same, what would the gravitational force on the astronaut by the moon? Okay, so this is just asking for one force. This is asking for the force between the moon and the astronaut themselves. So it doesn't really matter where the other one is. Um, it's going to stay the same. It doesn't really have a choice there on that. And the reason why that is because if you look back up at the top for the equation for universal gravitation, it only deals with a Newton's third law pair between two masses. So it's only asking you for one force. That force in and of itself doesn't increase or decrease depending on where the location of a third or fourth or fifth or sixth mass is. Notice that in this system case, they're only really asking about the astronaut and they're only asking about the moon. So that's where we get to stay the same. And in the justification of your answer, pay attention to that Newton's third law. That Newton's third law pair for universal gravitation. So there's only two masses inside that gmm over d squared. The big mass is going to be the mass of the moon, and the little mass is going to be the mass of the astronaut themselves. So the other one, so the mass of the planet, which we can call like MP, it doesn't show up. It isn't present in the formula. Can't spell present. There we go. Isn't present in the formula. Okay, for part C, let's see here. This one gives you a lot of space. Look at all this space. The astronaut's jetpack is powered by a reactor that can supply nearly limitless energy to the suit's thrusters. The astronaut wishes to escape this planet-moon system and travel to other parts of the solar system, away from any other significant gravitational effects or other planets or moons. Consider the energy required to escape from the configuration shown above. If the astronaut was instead standing on the moon, which not in the middle of space, but just standing on the moon, would it require more, less, or the same amount of energy to escape the system? So we kind of have to think about what the system is. So the system is the combination of the planet, the moon, and the astronaut themselves. And in the setup that they have up there, the astronaut is over on the left side. But what if they were over here, just like on the surface of the moon, would it take more energy in order to reach that, or less energy, or the same amount of energy? So, since we know that the force of gravity is related to that mass of the planets and the distance squared, that distance is going to be really important. Since you are closer to the surface of the moon, it's going to take more energy to get you off of that surface of the moon. So that is going to require more energy. So we're going to go ahead and say more energy. But then it says, hey, you know what? Justify your answer. You can use equations, but equations by themselves are insufficient. All right, so well then let's see what we can do. We know that there is a gravitational potential energy that exists for like moons and planets and stuff like that. And instead of it being like the force, GMM over distance squared, it's going to be something along the lines of like GMM over d instead, or the distance instead of the distance squared. So the potential energy for universal gravitation will work like this: little mass, big mass, and then it'll be divided by just the distance. It's a little bit different from the force of gravity. The gravitational potential energy is just, you have to get rid of one of those distance factors, and you get an answer in terms of joules. So it's going to take more energy to get you off of that planet because you are closer, and since the bottom has the denominator, the closer that you get to the planet's surface, the more energy it's going to take, the more gravitational potential energy you're going to have. So the more gravitational potential energy you have, the more you're going to have to spend in order to overcome that gravitational potential energy. Okay, I guess another good way to say that is if we talk about like the energy of the person in and of itself, like the total amount of energy, we're going to have to overcome two factors here. We're going to have to overcome the mass of the planet. So we're going to have G, the mass of the astronaut, times the mass of the planet. So I guess we'll say planet here. And that's going to be divided by, let's see, let's call that distance. We'll call it dp, the distance from the astronaut to the planet. So we're going to have to take that away in order to actually get this to have enough energy to move out away. But we're also going to have to worry about the gravitational potential energy of the mass of the astronaut and the mass of the moon as well. And then we're going to divide that by the radius. We'll call it RP or RM. How about, you know what? No, let's not use R. Let's just use D. The distance from the astronaut to the moon. So both of these, if we add all of these up together, the gravitational potential energy should be all that's required. So if we had those balanced out, then it would add up to a sum total of 0. That's something to think about. So you can explain this using this conservation of energy expression. Both of these gravitational potentials are going to have to be overcome. And think about how that would change depending on if you're like flat out on the moon, or if you're just kind of hanging out in the middle of space over here. So that energy will increase, so therefore it will take more energy for the astronaut to leave. So there's a lot of justifying to do there, so a lot to fill in that space, but this is in general what you would need to try to describe in order to get credit on that answer. And then let's see, moving on to I know there's a part D at least. All right, so it says, astronaut is able to travel a very far distance x away from the planet-moon system at a constant velocity. We need to underline that, constant velocity, because velocity being constant in space, if you're really close to a planet, it's going to be kind of weird to think about. Normally, whenever you put a force on something, there's an acceleration that happens because of it. It says it needs a total amount of energy, E, to do so. All right. Part 1, explain why the jetpack must do work on the astronaut to maintain a constant velocity. Well, if you're trying to get away from that planet, there's always this constant pull of gravity back towards you because gravity has an infinite range. So the jetpack, if it's pushing the direction, we'll just say that it's pushing to the right. If it's trying to get away from the planet, then it's going to have to constantly be supplying some kind of force in order to push it to the right, because there's going to be this pull of gravity back to the left constantly on you. So the jetpack's going to have to do work all the time to maintain a constant velocity, and that's what you need to try to include there. Okay, so try to include like the gravity's range, and also try to explain gravity's pull. because no matter what, it's always pulling on that astronaut. All right, and then that would be part of an explanation that you would need for that one. And I think that would actually work out really well. For part two, it says sketch a graph of the force exerted by the jetpack versus the position to keep the astronaut at a constant velocity as she moves away from the planet-moon system. Identify the feature of the graph that could be used to determine the energy used by the jetpack to move the astronaut in this manner. Okay, so let's see here. Let's go for this. Force is on the y-axis. Distance is on the x-axis. So if we were to try to make a, increasing force as the distance goes, if we were to try to make a straight line that goes this way, that really wouldn't really make that much sense because the force shouldn't need to increase as distance goes up because the gravitational pull goes down. In fact, the gravitational pull goes down in a relationship that is proportional to 1 over the distance squared, or 1 over x squared. So the jetpack is going to need to do the same thing. So if the gravity force is diminishing in an inverse r squared fashion, then that means that the jetpack is also going to have to diminish its force in an inverse r squared capacity as well too. So let's just put in a basic force. Let's go 1, 2, 3, 4, 5, 6, 7, 8 up. There we go. And if I double the distance, then it's going to get 4 times weaker. So 8 divided by 4 is 2. So I'm going to put another one down here for twice as much. And I'm going to just kind of try to draw an inverse r squared curve there. So that's generally what we're looking for the jetpack to be able to do. When you get a distance twice as far away, you're going to need to be 4 times weaker to get an inverse r squared relationship between the two. And then it says, identify the feature of the graph that could be used to determine the energy being used by the jetpack. Okay, so we know that the work being done is the energy that actually gets spent, and we know that that's force times displacement. So what we can do is we can use the area under the curve to represent the amount of energy that we need to spend, or how much energy that jetpack needs in order to get us to move away from the planet at a constant velocity. So we would need to know how much energy is there, and we can do that by finding the area under the curve. It'd be really hard to do for inverse r squared. We would have to do a little bit of calculus for it, but it's doable. Fortunately, they didn't ask us to. They just asked us to describe what mechanism we could use, not how to actually solve for it completely. So you would need to describe that with the area under the curve. You would need to describe that down here. Okay, let's see here. The next one, describe the power required from the jetpack as the astronaut travels away from the planet-moon system. So is it going to need more power as it goes away, or is it going to need less power as it goes away, or is it exactly the same regardless of the distance? And as you go, I would say that if you look at the graph above, as the distance increases between the two objects, the amount of force that the jetpack needs to exert lowers as you go along. So since power is related to the amount of work done, if you're lowering the amount of work done per second, then that's going to relate to less power as the distance increases as well. So, there's something that we could kind of do here, and that's if you're dealing with power, that's force times distance, or the work that's done over time. So we could also say that the power is equal to, let's see, mass times well, I guess we could, we don't have to do mass times acceleration. We can just do this. Look at the part above. See how this is distance over time? We could say that this is equal to force times velocity, but we've got to be careful because you can't use just instantaneous velocity. You would have to use the average velocity of the system, because this would only really work if you're dealing with a constant speed or a constant velocity. If you tried to use F times v for an accelerating system, the velocity would constantly be going up, and you would have to deal with like an area under the curve situation. So I'm going to put a bar over that v to kind of indicate that it's the average velocity. So since we could deal with that, looking back up here at the top, we can see how the force decreases. So if the force would decrease, then the amount of power would also decrease as well too. Okay, so we could do like any one of those justifications that you could have there. You could also explain it in terms of the velocity, and you could say, hey, you're going at a constant velocity, so as the force goes down, the power also has to go down as well. This is a great way to get that direct relationship between the two, and you don't have to worry about like extra variables that goes involved. In fact, if you did it with the force equals mass times acceleration, it would kind of be weird because if you're just looking at the astronaut by themselves, you get that the acceleration is zero because it's a constant speed. You don't really want to do that because you know that there is a force pushing on it. You just know that the net force just ends up being equal to zero. So there is a power there. So to justify your choice, I would explain how the power would actually work inside of this like constant velocity expression. So hope that helps you guys out, and I will talk at you later.